Functions can be represented algebraically, visually or graphically, numerically, or verbally. The goal of this video is to walk you through a concrete example so that you can see why these four representations are needed and how to recognize functions when they aren't represented as an equation. For our example, we are going to use data from the Sustainable Development Goals. These 17 goals are a blueprint for a sustainable future. Each one of the goals has targets, and each target is tracked by data. And we can find that data on the Sustainable Development Goal Tracker. So what you can see when you click on one of the goals in the tracker is the large goal and then a list of targets. Each target has a number of data sets that support the progress for that goal. So let's zero in on this one data set that is about the share of the population living in extreme poverty. If you'd like specific information about how that is calculated, you can find that information on the left-hand side here. On the right-hand side, we have data, so we can click on the chart. And it automatically populates with a number of countries. I'm going to go ahead and remove all those countries and just focus on the United States. I'm going to use the United States, partly because that's where I'm currently living and recording this, and partly because it has a nice data set that is fairly easy for us to use with the different representations. Now, this is a function. The share of the population living in extreme poverty is a function. We have our input and our output, and notice that for every input, we have one output, one unique output. So the input, or the independent variable, is located on our x-axis, and it is the year.
And we can denote the year by the variable t.
Our output, or our dependent variable, is located on the y-axis, and take note of the units, which is percent.
And we can use the notation p of t to represent the share of the population living in extreme poverty at time t.
This is the graphical representation of a function. We can also go to download and look at the data. So I'm going to go ahead and do that now. I'm going to download the data as a CSV file. That's a data file that can be read by Excel, Google Sheets, or Numbers. So I'm going to go ahead and download that, and it's going to download all the data. And I'm going to open it up in Excel, and I'm going to show you how we can represent this function numerically.
And what you'll see when you open the data is you have your first column, which is the country, the second column, which is the country code. Each country has its own code. And then I have my year. And then I have the share of the population living in extreme poverty. Now, I obviously have lots of different functions here because I have a function for each country. But for each country, my year is my independent variable, and I can call that year the variable t. The share of the population living in extreme poverty is a function of time, and I can denote that as p of t. So there I have my inputs, there I have my outputs. Again, each country is its own function. This is the numerical representation. Let's go back to our graph of our function and think about how we could represent this function using equations. Now, I picked the data from the United States because it is a fairly easy function in order to construct. They will not all be so easy. But what you can see when you look at this graph is that we have a piecewise linear function. So we have a bunch of lines that are connected. To make our construction of our equations easier, what we're going to do is we're going to let the year of 1979 correspond to t equals 0. So what that means is our independent variable, time, stands for the number of years since 1979. So, given that, we need to figure out what the equations are for all of our little line segments. You should go ahead and pause the video now and see if you can figure this out. I've just posted the equations, and you should take a second and make sure that they make sense to you. Notice that between the years 0 and 12, which corresponds to 0 and 12 years since 1979, the share of the population living in extreme poverty is 0.5%. Then we have found an equation for the percent of the population living in extreme poverty between t is equal to 12 and 15. We found that equation using the two endpoints, so basically having 2 points on a line, finding the slope and the y-intercept. Notice that between the year of 15 and 21, the share of the population living in extreme poverty was 0.7%, and so on. You should work through the calculations to confirm that you are comfortable finding the equations of these lines. Again, as a reminder, the t corresponds to the number of years since 1979. This is an algebraic representation of the function. And when we think of functions, we very frequently think of them in an equation form.
The final representation is the verbal representation. And we can describe this function with various levels of complexity. So we could say just that the share of the population living in extreme poverty in the United States is a function of time. Or we could say that the share of the population living in extreme poverty in the United States increases over time. Or we could say that the share of the population living in extreme poverty in the United States stays fairly constant, but increases about 0.25% every 5 to 10 years. So these are the four representations of functions: graphical, numerical, algebraic, and verbal. And as we learn calculus this semester, we will be learning calculus through all of these representations.